It's rare, but sometimes. Okay, it's working. Good. I'm on page 5. So I'm just going to copy 10, 15, 973, 11, 15, 844, and the last one, 12, 15, 739. Okay, so I'm going to stop sharing now. Where is my mouse? Okay, so I'm going to determine these two slopes. I'm going to call this M1, Y2 minus Y1. Of course, it's over 1. And I'm going to call this M2, 15,739 minus 15,844, of course, divided by 1. It appears, I didn't look at the numbers, but it appears to me that that was steeper than this. But you could be right. And I could be wrong. 973. Sometimes the answer, the graph may be deceiving. 739 minus 15844. Yes, so this is negative 129 per day, and this is negative 105. So the first one is steeper, 129, and this is negative 105. And this is dollars per day. It's not dollars, sorry, it's points. We're talking about Dow Jones. Yep, points per day. Good. Let's move on.
Would you list that? How would you list, because it's 10 to 11, so it's not one day. How would you list that it's that part of the slope?
What do you mean 10 to 11?
It says on what day did it show the greatest day of decrease, but we're saying it goes from 10 to 11. That's, you can't say
right.
Like, oh,
so
but
10. This is 15,973 is at the beginning of the 11th day, and 15,844 is at the end of the 11th day.
So you'd put the 11th day.
Correct.
Okay.
Yes. Is that better?
Yeah.
Perfect. We already did this. We found f prime for the given function for the square root of x, and we can do it for anything else. Let's go back to and see if there is anything else we want to look at. Yes. Okay, so also I would like to look at a word problem. Okay, find the equation of the secant line, find the average rate, repeat parts. If there is anything that is useful here, because everything, find the equation of the secant line is just a slope. Find the average rate of change, the same, just a slope. Approximate the rate. Okay. Let's see here. Yeah, let's look at a piecewise defined function again. These are also piecewise defined functions. The absolute value is always a piecewise defined function. Okay, let's look at 55. In 55, we are given a function, f of x, which is x squared plus 1 for x less than or equal to 2, and 2x plus 1 for x greater than 2. Verify that f is continuous. Okay, continuity. Perfect. And part B, differentiability at x equals 2. Okay, perfect. So let's take a look. Do we know that this is continuous no matter what? Do we know that this is continuous no matter what, and why? So in part A, x squared plus 1 and 2x plus 1 are continuous functions on everything, all real numbers. Why?
Polynomials.
Very good. As polynomial functions. Perfect. But what we don't know, we do not know about continuity at x equals 2. How do I write continuity at a point?
limit of f of x as x approaches a from the left
Good.
must equal
Which function? Which function exactly? So we don't have to write it twice.
f of x.
Which one exactly?
Oh.
Yeah, you're right.
So x squared
Absolutely. Equals the limit as x approaches 2 from the right. Of course, it must be the other one. And it has to equal f of 2. There are 3 parts to continuity at x equals 2. 3 parts. Okay, can anyone calculate this for us other than Nick?
They're both 5.
Very good. 2 squared, 4 plus 1 is 5. 2 times 2 plus 1 is 5. F of 2, of course, is one or the other. It's the first one, so it's 5. So yes, we say continuity at A, yes. Now let's look at differentiability. So we do know how to calculate. That's why I chose that function. It should be a quick answer. Can anyone give us the derivative of this? First, the derivative of x squared.
2x.
2x.
Good. But what is the rate of change of 1?
0.
Of course. If you have $1 in your pocket, it will never grow or decrease, right? So the derivative of x squared plus 1 is just 2x. For x less than 2. I cannot write the equal symbol here yet, because I don't know if the function is differentiable at 2. Now, this is a linear function. And without even knowing anything about calculus, you can determine the slope of this line. You know how. What is the slope of this line?
2.
Exactly, 2. This is the slope, and this is its derivative as well. It's a constant derivative for x greater than 2. So now, remember, this gives us the slope of the line, the slope of the tangent line, approaching 2. What does this equal to when x is closer to 2? What will the value be when x approaches 2 from the left? What will this equal to? If x approaches 2 from the left, this quantity will approach
0.
If 2 times 2 is 0, then yes.
4.
Of course, right? As x approaches 2 from the left, 2 times 2 will be 4. Agreed? Which means that when x is 2, so this is x equals 2, the left piece has a slope of 4. But what about the right piece? The slope for the right piece is
2.
2. Are they the same?
Nope.
No. So that's why I cannot put equal symbol here. And write f of x is not differentiable at x equals 2. It's not. It has a corner. This slope is steeper, has 4. This slope is smoother, just 2. So at this point, 2 comma 5, this is the point 2 comma 5 right here. F of 2 is 5. At this point, the slope on this side is 4, and the slope on this side of the tangent is 2. In other words, it's not a unique tangent, 2 tangents, which means the function is not differentiable at that point, although it is continuous. So here's a question for you, and then we'll continue. I know you are excited to look at the differentiation rules. I am too. So here is continuity, and here's differentiability. Is this true? Is this true? What am I saying? Continuity implies differentiability, or differentiability implies continuity, or both, in both directions. Continuity implies differentiability, differentiability implies continuity, or both.
I think it's just differentiability implies continuity, but not the.
Absolutely, this is the only one. If a function is continuous, everywhere, it doesn't have to be differentiable. But if it is differentiable, it must be continuous. Absolutely. Who said that?
Liam.
Thank you. The other one is false. This way, false. No. A function that is continuous and has no corners, no cusps, no vertical tangents, then is differentiable. So a lot of extra conditions. But if it is differentiable, it must be continuous, mandatory. Good, very good, awesome. So let's continue now with finally differentiation techniques. Okay, in other words, 1.5, differentiation rules. Okay, so one of your colleagues already mentioned, if we have x to a power, any power, n, lowercase n, prime, we bring n in front and we multiply by x, subtracting 1 from the power, just 1. So that's why our x squared prime was, with differentiation rules, very easy, 2x. If we have a constant times a function prime, if it's multiplied, if it's a factor, the constant stays and we only differentiate the function. If we have a sum of two functions or a difference of two functions, no problem. We'll have f prime plus or minus g prime. And I will give examples from all these, or I'll let you pick if you want. Now, of course, we already know the square root. Please remember it forever, please. 1/2 the square root of x. And I'm going to add here, although we may not be able to do a lot with them today. They are in the next section, okay, in 1.6. So we have them here, and then we'll practice as much as you want. 1.6, product and quotient rules. So do not assume anything here. You just have to memorize the rule. When we have two functions multiplied, we differentiate the first function multiplied by the second one as is, and then plus, we copy the first function and multiply by the second one prime. This is the rule that I recommend. You can choose the reverse one, whatever. Why I recommend this is because I always like to keep them in the correct order. 1, 2. 1 prime, 1 being the first function, 2 being the second function. 1 prime times 2 plus 1 times 2 prime. If you want to reverse these two, you can do whatever you want. It's fine by me. But do not attempt to do anything else. The product rule is this. The quotient rule, very similar. I'm on 7. The quotient rule is very similar, but it's a ratio, of course. F of a g prime. I copy the same thing I see here, but with minus. So f prime g minus f times g prime. The denominator is never differentiated. You just copy it and square it. With 1, 2, 1, 2, 1/2. 1 prime times 2 minus 1 times 2 prime over 2 squared. 1 and 2. It's up to you. If you want to twist anything here, it's fine.